this video, we're going to talk about limits. Introduction to limits. If you come upon something that says this, for example, this is read as, that there means limit. The limit as. Read it that way. Limit as. This is read as x approaches 3. So this whole thing is the limit as x approaches 3 of that function of x plus 2. The limit as x goes to 7 of 3x plus 4 to the 5th power. It's read as, this means the limit as x, I can put a different letter there, as x approaches that number 7 of this 3x plus 4 to the 5th. Okay. Now, let us look at this first limit that I wrote. Now, as it says, oops, I forgot to write 3. X approaches 3. It never reaches 3. It can get exceptionally close to 3, but not 3 itself. And I want to know what this is getting closer to. So let's have this table. We have x values and f of x values. F of x in this case is x plus 2. And we want to see what happens as x gets closer and closer to 3. So maybe first I let x be 2.9 and then 2.99 and then 2.999. Now that's from a little bit less than 3. For example, if 3 is right here, I'm getting closer and closer to 3. First I'm 2.9 and then here is maybe 2.99 and here is 2.999. But I can get close to 3 from the other way as well. How about first 3.1. Oops, I meant to put it there. I'm 3.1. That's not very close to 3. Just like 2.9 wasn't very close to 3. But then I go to 3.01 and then 3.001 and finally 3.001. Now remember, f of x is x plus 2. That is, you take the x value and you add 2. If that's the x value 2.9, I add 2 to it, I get 4.9. If that was the x value 2.99, I add 2 to it, I get 4.99. If this were the x value, I add 2 to it, I get 4.999. 4.999. Now, if x is 3.1 and I add 2 to it, I get 5.1. If x is 3.01 and I add 2 to it, I get 5.01. Nothing hard yet. If x is 3.001 and I add 2 to it, I get 5.001. And if I add 2 to the last one, I'll get 5. Oops, this should be 0, 1. I get 5.0001. Notice that these numbers are approaching 3 from above. Okay, but nonetheless, when I approach 3 from numbers below 3, these numbers are below 3, but I'm approaching 3. The function is approaching 5. When I am a little bit more than 3 and then closer to 3, but still above, and even closer to 3 and closer to 3, I'm also approaching 5. That tells me that this limit is 5. The answer to this question is 5. In this case, you could have just plugged in 3 for x and gotten the answer. Let us look at another one. Suppose you have the limit as x approaches 2 of x squared minus 4 over x minus 2. Well, if you plug in 2, you get 2 squared minus 4 over 2 minus 2, which is 4 minus 4 over 2 minus 2, which is 0 over 0, which is not allowed. It's called indeterminate. Okay. Well, if you look at this more closely, so 2 from pre-calc, if 2 makes the top 0, then x minus 2 must be a factor. And it turns out the other factor is x plus 2. And if 2 makes the bottom 0, then x minus 2 must be a factor. In fact, it's the only factor. Now, so x over x is not 1. I don't care what your teachers may have told you. If they told you it's 1, they honestly are wrong. It's 1 if x is not 0. Because if x is 0, 0 over 0 is not 1. It is indeterminate if x is 0. Now, same thing with x minus 2 over x minus 2. As long as this is not 0 over 0, you get 1. But when do you get 0 over 0? When x is 2, not 0. 0 minus 2 over 0 minus 2 is negative 2 over negative 2 is 1. Okay, but if x is 2, x minus 2, that's 0 over 0. So you get indeterminate if x is not 2 for the top. You get 0 over 0 if x is 2. Okay? But the great thing about limits is if x is approaching 2, x won't ever be 2. X may equal 1.9999934. X may equal 2.0000000013, but it won't be 2. If x is not 2, this mess is 1. So you can cross it out, and then you just take the limit of x plus 2, which is 4, because I plug 2 in, I add 2, I get 4. What is going on here is that this function, which happened to be the one above, not factored, is the same as this function, except at 2. This is undefined at 2. Okay? So, if you were to draw this function it will look just like x plus 2. Y-intercept of 2, slope of 1. It will look exactly like this, with one exception. At 2, you have an open circle. It's not defined. But the bottom line is, if x is really, really close to 2, that's going to be just below 4. If x is a little bit more than 2, that's going to be a little bit more than 4. It's approaching 4. It's approaching 4. In fact, it's approaching what that number would have been if it wasn't, it would be what that number would be if it was defined at 2, just like this one. These two functions, they're not equal, but they equal everywhere except 2. They're equal everywhere except 2. But since they're not equal at 2, they're not equal. But I don't want to be 2. I want to be really close to 2. So I can use this function because as long as I'm not at 2, yes, these two functions are equal. That is, this function and this function here, they are equal except at 2. Okay, well, at 2, this is 4. That's the answer. As I get closer and closer to 2, closer to 2, closer to x equal to, closer to x equal to, around here, around here, around there, around there, and coming from the other direction, as x gets closer and closer to 2, the y values approach 4. So we say the limit equals 4. Okay, this limit is equal to this limit because all I did was factor, which is equal to this limit because this function here and this function here are exactly the same except at 2. But I don't care what happens at 2. X will never be 2. It'll get close to 2, but it won't equal 2. Okay. Now, I just want to show you that what I'm saying is really true. If only this thing would scroll down. So we have that, or what do we have? We have x squared minus 4 over x minus 2, which is x minus 2 times x plus 2 over x minus 2. Now, if you plug in another number, so suppose x is 7. So you're going to get 7 minus 2 times 7 plus 2 over 7 minus 2. That is, you're going to get 5 times 7 over 5. This is going to cancel. That is, that's going to cancel. Oops, 7 plus 2 is 9, excuse me. You're going to get 9. That is, you could have just used the rule x plus 2, plug in 7 for x, so plug in 7 for x, and get 9. The same answer. Because this will always cancel out to 1. No matter what number you plug in, I'll plug in 10 now. 10 minus 2 times 10 plus 2 over 10 minus 2. Well, this is 8 times 12 over 8. Oh, look at this. This cancels out. I could have just used 10 plus 2 and I would have gotten the same 12. That is, this function, which is exactly this function, is equal to x plus 2 if x is not 2. Not that 2, but what makes this 0? Okay, they're the same two functions. In fact, this function that we have is a piecewise function. If you have x squared minus 4 over x minus 2, this becomes x minus 2 times x plus 2 all over x minus 2. Now this is a piecewise function. When this cancels out, you just get x plus 2. But that cancels out if x is not 2. Because any number take away 2, a number that isn't 2, when you take away 2, you won't have 0. In fact, you'll have the same non-zero number in the bottom, and whatever that number is, when you divide it by itself, it cancels out. But if you plug in 2 for x, if you do plug in 2 for x minus 2, x minus 2. In the top, you're going to have 0 times 4, which is 0. And in the bottom, you'll have 0, which is indeterminate if x is 2. This is a piecewise function. Most times, it's x plus 2. But not when x is 2, it's indeterminate. So when I ask you for the limit as x goes to 2 of this mess, and you know equals the limit as x goes to 2 of maybe something else. Well, you know that this is equal to when x is not 2. All I know is x is not 2. Oh, this function is equal to x plus 2 when x is not 2. And if you're really, really close to 2, because it tells me that x is close to 2, and you add 2, you get really, really close to 4. It approaches 4. Okay. Let us look at another problem. Suppose you have k of x. It's just a name k. They don't all have to be f and g and h. Suppose k of x is 1 over x minus 2 plus 1. Now, you should know how to draw 1 over x. You go to the origin and it goes like this and like that. Okay, but this time the vertex is not the origin. What makes this 0 is 2, and what that says is 1. So from pre-calc, you should know that the vertex is at 2, 1. So I go to 2, 1, and I make believe that this here is the new origin. And I want to go like this, and I want to go like that near the new origin. So this is no problem. What's a little bit of a problem, let me draw it over here since it's a problem. You know, when I go like this, should I cross when y is negative? Should I cross at exactly 0? Should I cross at exactly some positive number? Well, in all 3 cases, the x value is 0. Why? Because whenever you're on the y-axis, x is 0. The x value along here is 0. Okay, so plug in 0. What is k of 0? It is 1 over 0 minus 2 plus 1, which is 1 over negative 2, which is negative a half, plus 1, which is a half. Okay, I now know that I cross at 1/2. So, for the other portion of the graph, I'm going to draw it this way. And that is the graph. Now, the question is, what is the limit as x gets closer and closer to 2 of k of x? What does this equal? Well, if you approach 2 from the left, if you approach, sorry, from the right, I'm always above 2. If you approach 2 from above 2, it looks to me like it's going to plus infinity. But now, if you approach 2 from below 2, getting closer and closer to 2, but those numbers are all less than 2. The y value is here and then here and here and here. But as x gets closer and closer to 2, it's going to negative infinity. I don't care. So these numbers different. I don't care if they're infinity or not. If these two numbers differ, then you say the limit does not exist. It could have been that this one is going towards 7 and this one's going towards -3. They're not the same y value. Okay? In other words, if the graph looks something like this, here's 2 and here's 7 and here's -3, maybe from the left the graph goes like that and it stops right there. That's at 2. And the other graph, the other side above 2, it goes like this and then it stops right there. Well, if you're a little bit above 2, you're getting closer and closer to 7. But if you're a little bit less than 2, if you're getting closer and closer to 2, but always less than 2, the y value is getting closer and closer to -3. If you don't get the same answers from the left side and the right side, we say the limit does not exist. Okay. Now, most times when it comes to limits, you're gonna directly substitute. So if you were asked to find the limit as x goes to -3 of x squared plus 5 over x minus 2, you would do x, because x, I'm going to plug in -3 for x. I'll even call it x. X squared plus 5 over x minus 2. That's 9 plus 5 over -5, which is 14 over -5, which is -14/5. That problem is done. Let us talk about some rules of limits. If you have the limit as x approaches some number, let's call it c, of two functions, f of x plus g of x. You know, it may be x squared plus x cubed. Okay? This is equal to the limit as x goes to c of f of x. Calculate that answer and then add on the limit as x goes to c of g of x. What this is saying is that the limit can distribute over addition. And you know what? We have the same thing for subtraction. If you have f of x minus g of x, the limit of that, you can take the limit of the first function, whatever that is, as x goes to c, and then subtract the limit of the second function. Very, very friendly limits. So, for example, if f of x was to be x squared plus 3, and g of x is 4 over x, and c is 2, what is the limit as x goes to 2, because c is 2, nothing more than that, of f of x plus g of x? Well, the rule says that you can take the limit as x goes to 2 of f of x, calculate that, and then add the limit as x goes to 2 of g of x. Okay, well, this is the limit as x goes to 2 of f of x, which is that, x squared plus 3, plus the limit as x goes to 2 of g of x, which is 4 over x, and calculate these two separately, and in the end, add them together. So we'll get 2 squared plus 3, which is 4 plus 3 for the first limit, which is 7, plus, plug in 2 for x, you get 4 over 2, which is 2. 7 plus 2 is 9. The only time you have where limits are a little bit hard, or harder, is when it's undefined. When you plug in 2 here, when you plug 2 in, and you get 0 over 0. That gives you a problem, or if you get infinity. Okay. Now, if all I did was change this problem to subtraction, there's no big deal. It'll just be minus. It'll be minus. This will still be the same. This will still be the same, but this time I'm subtracting. 7 minus 2 is 5. This limit, oh, I should change it here as well. Sorry. Glad I checked. This limit right here would equal to the number 5. And when it said plus, it would have equaled to 7 plus 2, which was 9. So this is one rule right here. Actually, yeah, up here, these are 2 rules that you should know. And rule 1, rule 2 is very friendly. You have subtraction, take the limit of the first, minus the limit of the second. Okay, kind of what I did here. I took the limit of this, which was 2 squared, and I added on the limit of this, which we'll talk about in a moment, which is 3. And 2 squared happened to be 4, and 3 happens to be 3, and 4 plus 3 is 7. Now, before we talk about the limit of just a constant, let's talk about a product and division. If you have the limit as x goes to c of f of x times g of x, well, this is nothing more than the limit as x goes to c of f of x. Get that answer. And then take the limit as x goes to c of g of x. Get that answer. And as I denoted, multiply the two. So, for example, if you had the limit as x goes to 3 of x plus 4 times x squared minus 5. You can think of this as f of x, like that, f of x, and you can think of this as g of x if you like. So this becomes the limit as x approaches 3 of the first function. Oops, let's keep it the same, x plus 4, and this answer gets multiplied. So I did the limit of this times the limit of that times the limit as x goes to 3 of x squared minus 5. If I directly substitute 3 for x, I get 3 plus 4 times If I directly substitute, I get 3 squared minus 9. 3 plus 4 is 7. 9 minus 5 is 4. It's 7 times 4, which is 28. Now, this is a rule, and let's call it rule number 3. You don't have to even use this rule to do this problem right here. You have the limit as x goes to 3 of x plus 4, x squared minus 5, regardless of what people tell you. I promise you they're wrong. Always, always direct substitute. So you get x, I'm going to write x that way. You get x plus 4 times x squared minus 5. Exactly what I had here. And I never really broke it up. I never said, oh, I'm going to take the limit of this and the limit of that and multiply. But it turns out that's what's happening. This is 7. This is 9 minus 5, which is 4. And I still get the same 28. I take it there may be times, well, I shouldn't say I take it. There will be times when you do want to break this up as the limit of one factor times the limit of the other factor. This and that are the factors. Okay, now we have a similar rule for division. We'll call it rule number 4. The limit as x goes to c of f of x over g of x is equal to the limit as x goes to c of f of x divided by the limit as x goes to c of g of x, provided that the limit as x goes to c of g of x is not 0. Okay, if this bottom is not 0, it's okay. You can do this. So, for example, if you have the limit of as x goes to 2 of x, well, let's go to 3. X goes to 3 of this problem. Okay? You cannot say that this is the limit. You know, let's make it plus 9. You cannot say, well, actually, let's keep it minus. I apologize. You cannot say it's the limit as x goes to 3 of x squared minus 9 over the limit as x goes to 3 of x minus 3. And the reason is the bottom is 0. Turns out the top is 0 too, but that didn't matter. Okay, so since that's wrong, let's do it the right way. Well, when you plug in 3, you get 0, and you plug in 3, you get 0 here. That means that x minus 3 must be a factor for the top, and you have to get good in factoring. The other factor is x plus 3, and the bottom, if x equals 3 makes this bottom 0, then x minus 3 must be a factor. It turns out it's the only factor. Now, the only time this is not 1 is when x is 3. Because if x is 3, you'd have 0 over 0. Oh, how nice. X is not 3. For right now, it's not 3. That is, you can cancel this out as if it's 1. So it becomes a limit as x goes to 3 of, well, the 1's cancel. The x minus 3 cancels out to 1. So you just left with x plus 3. And if you plug in 3 for x, you get 3 plus 3, or 6. This function is exactly this function when x is not 3. Okay, and x is not 3. It's getting really close to 3, but not 3. Understand, that a number really close to 3, like 3.0000014, is not 3. And a number just below 3, 2.999999, a lot more nines, but it ends. This is not 3. Fair enough, they're close to 3. You know, this number minus 3 is 0.00, you know, a lot of zeros, and then 1, 4. And the bottom is also the same number of zeros. That's 1. It's just 0 over 0 that causes the problem. And that happens when x is 3. Okay. So you are not able to use this rule to get the answer. Why? Because the bottom limit was 0. This limit equals 0. And that's why we say no, they're not equal. I suspect that there's times he may luck out where it wasn't a problem. But, you know, why gamble? It's not equal. You know, if you think that 7 cubed means 7 times 3, which is 21, well, you're wrong. But in this case, you know, if you did 2 times 2, yeah, it's right. You were lucky. You were lucky. Okay? And you don't want to get the right answers by lucking out. Okay. Now, let us talk about another limit rule. What happens as x approaches a number, say c, of a constant? So that's the function. F of x is, f of x is equal to a constant. Well, how does that function look? Remember, f of x is y, so y is always the same number. So y is always the same. I know it is. What's the y value here? Just look to the right. It's that number, say k. What's the y value here? Just look to the right and read it off. It's k. What's the y value here? Just look to the y value, read it off. What's the y value here? Just look to the y-axis and read it off. The y value here, k. The y value here is k. Now, if this is c, so I'm going to travel along this line. I'm going to travel along this line, and I'm going to get really close to c, just a little bit less than c. Right there. Well, the y value right here is k. In fact, every blue dot, the y value is k. Now, let me get to c from a little bit more than c. Let me approach c. So, I'm more than c. I'm a little bit closer to c. I'm closer to c. I'm really getting close to c. Now, I'm really narrowing in on c. Oh, well, why am I playing as if c is there? I apologize. Let me try this again, just in case it sounded confusing. So here is c, here's a little bit less than c, here's a little bit more than c, and y is always k. So if I, right at that point, whether that point's on the graph or not, I'm just saying that's right above c. Okay, if I start getting closer and closer to c, get closer and closer to c. I'm getting closer and closer to c, just not very close yet. But now I'm getting very close to c. And the y value is near k. If I'm above c, but I move towards C. The y value, about right here is also k. This limit is just k. K doesn't care what's happening to x. K is always k. For example, if I tell you that f of x is k, like 7 or 23 or pi, what would f of 2 be? Well, the rule is write this down exactly the way it is, and wherever you see k, x, if you see x, plug in a 2. And I did that. I wrote this down exactly the way it is, except wherever I saw x, I wrote 2. And this is what I came up with. What is f for 3? Well, I'm going to write this down exactly the way it is, with one exception. Wherever I see x, I'm going to put 3. There it is. It's always that. Just like if you were told that f of x was x squared plus 4x plus 1. What is f of 3? Well, you're going to write this down exactly the way it is, with one exception. Wherever you see x, you're going to plug 3. So you're going to, I'll even say x. I get x squared plus 4 times x plus 1. 9 plus 12, 21 plus 1, 22. But if there is no x's, I just get back k. Okay, so no matter where I am on the x-axis, near k, not near k, this k is always k. It doesn't care about x. So that's a rule. I think we're up to rule number 5. The limit is x goes to c of a constant is equal to a constant. K is a constant, like 7 or pi or e squared. Okay. Now, let us finish this by doing one more type of problem. Suppose you were asked to compute the limit as x goes to c of a constant times f of x. Well, that's a product. So let's use that product rule. So the limit is x goes to c of k times the limit as x goes to c of f of x. Now, the first limit we know, it's k. This limit we don't know, because we don't know what f of x is, we don't know what c is. So the best we can do is say it's this. And then you say to yourself, oh, you look from here to here. And you say, oh, the constant can come out in front. It's not because I told you, but it's because we proved it using the product rule. So if you ever have the limit as x goes to 5 of 7 times x squared minus 1, if you like, you could do it this way. That is, it's 7 times that limit. And that limit is 5 squared minus 1. This is 24, and 7 times 24 is, I guess, 168. What I do is, 24 is the same as 20 plus 4. So I get 140 plus 28. So adding 28 is the same as adding 20 and then 8. 140 to add 20. 140, 150, 160 plus 8. In fact, I don't even write down 20 plus 4. I know that this is 20 plus 4. I just do 7 times 20 is 140, because I know that 2 is really 20. And then I do 7 times 4 is 28. And in my head, I add those two numbers and I get 168. Even if I couldn't add this in my head, I would say 140 plus 28 and then write it down and figure it out. I mean, after all, if you did it this way, you'd have 28, and then 7 times 2, well, that's the 140. You're going to still have to know that. Okay. Let us look at another rule. So here was the 5th rule. Now, the next rule really comes from an earlier rule. Call it number 6, I think. The limit as x goes to c of f of x to the nth power, what you can do is just calculate the limit as x goes to c of f of x, and whatever you get, raise that to the nth power. Now, this rule should be obvious from the earlier one, because the limit is x goes to c of f of x to the nth power. Well, this here is the same as f of x times f of x to the n minus first power. Okay, now the rule tells us, the product rule says, you can take the limit of the first, and that is the limit of f of x, times the limit of the second function, f of x to the n minus 1. Okay, so I'm going to write down the first limit. The limit is x goes to c of f of x. And now for the second limit, I'm just going to change the way I write the function. F of x to the n minus 1 is f of x times f of x to the n minus 2. And then I still have this first function at the far left times a limit of a product. I can take the limit of the first times the limit of the second. So I get the limit of the first, and then I multiply that by the limit of the second, which is f of x to the n minus 2. And that equals to, well, this and this, they're the same limit. They're the exact same limit. So whatever this limit is, since I'm multiplying it by itself 2 times, I'll get squared. And this limit, I can think of it as the limit as x goes to c. That is, this function I can think of as f of x times f of x raised to the n minus 3. And I can keep playing this game. Get the limit as x goes to c of f of x squared, this first limit, times the limit of the first times the limit of the second. The limit is x goes to c of f of x times the limit as x goes to c of this function, f of x to the n minus 3. All right, I'm multiplying this by itself. This one 2 times and this one 1 time. You know, just like x squared times x is x cubed. This is a real number. So I'm going to get the limit as x goes to c of f of x raised to the 3rd power times this. And if we just keep breaking up this limit with the power, if we keep doing this, we'll eventually get the limit as x goes to c of f of x to the nth power. You can prove this by induction, but here was a quick argument that shows that what I'm saying is most probably true. Okay. So let us do an example or two using this method. Suppose that you're told that the limit as x goes to 8 of, not told, I was thinking of another problem. Suppose you were asked to do this limit. What is the limit as x goes to 8 of x plus 2 cubed? I mean, sure, you can do x plus 2 and cube it, and then you'll get 10 cubed or 1,000. But sometimes it won't be as friendly to put the 3 in yet. So you can just take the limit as x goes to 8 of x plus 2 and then cube that answer. Well, when you plug in 8, you're going to get 8 plus 2, which equals 10. But then you have to cube that answer. So yes, we're getting the same answer. But sometimes it'll be best, in your best interest, to just compute the limit without the power and then put in the power. Trust me, it'll come up. Now, let us try this last set of problems. Suppose you're told that the limit as x goes to c of g of x is equal to 7, and the limit as x goes to c of f of x is 2. Okay, so this is, quote, given. And you want to find, say, these 3 or 4 limits. What is the limit as x goes to c of f of x cubed? Let's actually write them all down. What is the limit as x goes to c of f of x over g of x? And what is the limit as x goes to c of 8 times g of x? And one more. What about the limit as x goes to c of 4 times f of x minus 2 times g of x? Okay. Now, here's a case where you can't do this first one unless you use that theorem. This first one is the same as the limit as x goes to c of f of x, and I cube that. Well, I know what this limit is. They told me that it's 2. So I get 2 cubed, which is 8. But there will be real limits where they tell you what f of x is, and they ask you for the limit as x goes to 7 of whatever f of x is cubed, and you're really going to want to find the limit before you cube it. Okay, so we have it, it's 8. Now, this here is equal to the limit as x goes to c of f of x divided by the limit as x goes to c of g of x, provided the bottom limit is not 0. But they're telling me what the bottom limit is. It's 7. And the top limit, they tell me it's 2. That one's done. The next problem is, this is k times a function. The limit of k times a function. Rule says that you can factor out the k. Then you take the limit as x goes to c of g of x. Well, 8 is 8, and this limit is 7. 8 times 7, 56. The last one. This minus that. So it's the limit of the first term, that limit, minus the limit of the second term. as x goes to c, and the second term is 2 times g of x. Now, just like we did with this one up here, this 4 can come in front. So it's 4 times the limit as x goes to c of f of x. And the reason you want to do that is because they told us what this limit is. They told us this limit is 2 minus, let's pull the 2 in front again, with a constant in front again. And then you multiply that by the limit of g of x. But the nice thing is they told us what that limit is. That limit is 7. So we have 8 minus 14, which is -6. This limit right here is equal to -6. Okay, that finishes the video entitled An Introduction to Limits. The next video, we'll start doing some more rigorous limits, but we got a lot of the rules out of the way in this video. Do lots of problems.